the
This
consumer
conference
and
will
also
now be
the
recorded.
utility, and also the illustrative examples. You should always remember that with respect to the fundamental waveform, whenever the higher order harmonics are superimposed, okay, the overall voltage and the current waveforms get distorted. Harmonic currents are introduced because of the non-linearity loads, non-linearity in the loads, non-linear loads. For example, a power electronic equipment, a 6-pulse or a 12-pulse converter, electric arc furnace, and also the welding machines, the switched mode power supply, they all introduce actually the harmonics to the system. The effect of the harmonics, I am not going in depth. It is going to increase the losses in the system. There will be communication interference. Equipment gets overloaded. Insulation degradation will happen. Therefore, we would like to know how to do the harmonic simulation using the MiPower software, and also to understand some of the fundamental concepts with respect to the harmonic analysis. There is a standard from IEEE 5192014 that talks about the various harmonic limits. Therefore, we will also try to interpret what is that harmonic limits as described by the IEEE also. First and foremost thing is, fundamental component of the current flows from the source to load. This is what we need to understand. The fundamental component of the current flows from the source to the load, while the harmonic current flows from the load to the source. Therefore, if there is a load here, assume that actually it's a rated current at 100 MVA base, okay? The 437 ampere, assume that this is the inductive current being drawn by the load. The voltage here is 1 per unit. 100 MVA 10% impedance is the transformer impedance. Therefore, when you draw the inductive current of 1 per unit, because on this you are drawing the 100 MVA current, 1 per unit current on 0.1 per unit. Therefore, the voltage drop will be 0.1 per unit. Therefore, at the PCC, if the voltage is 1 per unit, at the plant, voltage will be 0.9 per unit. Therefore, at fundamental frequency, voltage is maximum at the source and minimum at the load. This is what you need to understand from the source to the load. But for the transformer tap, capacitor, the line charging susceptance, the voltage keeps on falling, and at the source, voltage is maximum. For the fundamental frequency, voltage keeps on falling and it is minimum at the load point. Now let us see what happens for the harmonic current. Harmonic current flows from the load to the source. Assume that the fundamental current is 100%. Fifth harmonic current you are injecting. This is a nonlinear load which is injecting the fifth harmonic current, which is 10%. When you inject this 10% fifth harmonic current, what will happen? Let us see. Assume that the source is ideal source. The source is ideal. What you mean by the ideal source is impedance is very low, fault level is very high. Very high fault level and the impedance is very low means it is an ideal source. Therefore, we are considering an ideal source at 100 MVA 10% transformer and injecting actually 10% fifth harmonic current here. Now let us see in this equivalent circuit what happens. You are injecting the fifth harmonic current which is 0.1 per unit. This is the advantage of working with the per unit calculation. Very simple, so that you can just try to multiply. But I always suggest try to have a feel for the actual numerical values also. Therefore, when you are injecting fifth harmonic current of 0.1 per unit here, at the fundamental frequency, the impedance is 0.1%, 0.1 per unit, because 10% that is 0.1 per unit. At the fifth harmonic frequency, the transformer impedance will be XL is equal to 2 pi FL. Therefore, XL is equal to N into 2 pi FL, where F corresponds to the 50 Hertz. Therefore, N corresponds to 5. Therefore, at the fifth harmonic, the impedance becomes 0.5 per unit. With this 0.5 per unit, you are injecting a 0.1 per unit current here. Therefore, the fifth harmonic voltage at this bus at the plant will be 0.05 per unit. At the source, it is an ideal generator. Therefore, within the machine, there is no fifth harmonic voltage. Therefore, what it means is, at harmonic frequency, voltage is maximum at the load and it is minimum at the source. Therefore, whenever the harmonic current is flowing from the load to the source, voltage is maximum at the load point and it keeps on dropping and it can be minimum at the source. Therefore, this is what will happen in the harmonic power flow. Therefore, compared to the fundamental frequency, when we tell the harmonic currents are getting injected at the load point, and then they try to find out the shunt path. Wherever there is a shunt path, it will try to flow there. If it sees a very high impedance, it will oppose. If it sees a very low impedance, it tries to get drained there. That is how actually the harmonic power flow is going to happen in the given network. Now, IEEE 519-2014. In fact, in India, CEA has passed the regulation, means there is a guideline that for all the harmonic current measurement, injection, and also the analysis, penalty, everything, IEEE 519-2014 guideline should be adhered. If at all you don't have a copy of the IEEE, you can always procure that. Therefore, in that current distortion limits for the system rated from 120 volt to through 69 kV is available. What the guidelines talks about is, it talks about what is the harmonic current that is acceptable limit. How much harmonic current you can inject corresponding to the short circuit level divided by the load current. That is the ISC by IL. That is going to tell you how strong is your grid. For example, ISC by IL is 20. What it means is, your system is not that strong. ISC by IL is 1000, means with respect to the load current, the source fault level is very, very high. Source fault level is very high means impedance is low. Therefore, you are allowing higher harmonic current injection. If the source fault level is less, that is ISC by IL is up to 20, less than 20, the third harmonic to the 11th harmonic current that is acceptable is about 4%. Therefore, this is what actually the standard talks about. Again, I will repeat, if the source fault level is less, because the impedance is high, you are allowing less fault current to get injected. When the source fault level is very high, that is the ISC by IL ratio is very high, which implies impedance is low. In order to get the same voltage distortion, you can push more harmonic current. Therefore, for higher ISC by IL, higher of the current injection is allowed. What are the voltage distortion limits? Again, 69 kV to 161 kV, individual harmonic, we talk about the distortion of about 1.5% and the total harmonic distortion is about 2.5%. Throughout my lecture, even though the harmonic distortion THD is being referred for the voltage, and I am referring throughout my lecture TDD for the demand distortion, or the total current distortion is referred as TDD, and THD in my lecture we are talking about the total harmonic distortion with respect to the voltage. But whether it is a harmonic distortion, total harmonic distortion, some people refer it as THDV, telling that it is a voltage related distortion. THDI with respect to the current distortion with respect to the current measured current, and TDD, that is with respect to the demand distortion with respect to the maximum load current. Whenever you measure the harmonic distortion, most of the measuring instruments, they give actually the current distortion with respect to the fundamental current measured at that instant. Therefore, that is what we call it as THT. But when you measure that current with respect to the maximum load current, then actually the distortion may be lower. Therefore, whenever you are using the harmonic instrument, you have to be very careful whether the current that you are measured is with respect to the current at respect to the fundamental current or the maximum demand current. Therefore, whenever the IEEE talks about the IEEE 519-2014, the standard is very clear. It is with respect to the maximum demand current. Similarly, the current distortion for the systems rated from 69 kV through 161 kV is available, where actually at the higher voltage level, the current distortion limits are lower because many consumers are getting connected there. Therefore, the voltage distortion, because whenever you have a higher current distortion, which is a cause, effect of that is higher voltage distortion. One is the cause, other one is the effect. Therefore, whenever you try to inject more and more current at the higher voltage level, the voltage distortion is going to be there. And when you have the higher voltage distortion at the higher voltage, many consumers below are getting affected. Therefore, whenever it is higher voltage, the current distortion is less. Now let us try to understand how to interpret this distortion. Let us take the example of the IEEE 514, okay, and then try to find out how actually this distortion is going to affect. We'll try to take the limits with respect to the 5th, 7th up to 29th harmonic and consider ISC by I load as 10. That is short circuit current divided by the load current, that is the ratio is 10. For example, if the short circuit current is 5 kiloampere, load current is 500 ampere, ISC by IL will be 10. Now, at the fundamental frequency, ISC by IL is 10. What it means? The source impedance becomes 0.1 per unit. If at all you are getting a ratio ISC by IL as 10, means the fault current is 10 per unit. Then the impedance is 1 by 10. Therefore, that is about 0.1 per unit. Therefore, with respect to the load current, with respect to the base of the load current, the source impedance will be 0.1 per unit at fundamental. That is 1 by 10. Now, corresponding to the 5th harmonic, XL is equal to 2 pi FL. At the 5th harmonic, this 0.1 per unit becomes 0.5 per unit, assuming that the source impedance is varying proportional to the frequency. Assuming that source impedance is varying proportional to the frequency, at the 5th harmonic, the impedance becomes 0.5 per unit, 7th it becomes 0.7, and at 29th it becomes 2.9 per unit. What is the harmonic percentage maximum value as per the IEEE standard? Okay. What is the maximum? Therefore, when you try to look into that, the various harmonic currents that have been explained here, okay, corresponding to the various voltage level, okay, what all that are acceptable. Based upon that, the acceptable limits are also available here. That is, a harmonic percentage maximum value as per the IEEE standard is corresponding to the 5th and the 7th, it is 2, 11th and 13th, it is 1, 17 and 19.75, and so on. Now, what is the voltage distortion you are going to get? This is the percentage current multiplied by the per unit voltage is going to give you what is the percentage voltage distortion. Because current in percent, 2 into 0.5, okay, that is the distortion you are going to get. Similarly, at the 29th harmonic, source impedance is 2.9. The acceptable current distortion is 0.3%. Therefore, the voltage that you are going to get is 0.87%. Now let us see what is the total demand distortion. total demand distortion is square root of individual harmonic current distortion. Therefore, current distortion is 2, 2 square is 4, therefore again 2 square is 4, 0.3 square is 0.09, square root of these values here, IH into IH. Therefore, the total demand distortion is square root of IH5 square, IH7 square, IH11 square. Therefore, the square root of that corresponds to 3.38. What is acceptable as per the IEEE limit? Acceptable as per the IEEE limit is 2.5. Therefore, if all the individual current distortions are maximum corresponding to ISC by I load of 10, then the current distortion will be more compared to the acceptable IEEE limit. Similarly, the total harmonic distortion with respect to the voltage is 3.36. Again, it is not acceptable. How it is computed? Individual voltage distortions are there. Take the square of that and take the square root of that. You are going to get 3.36. Again, it is not acceptable because the TST limit percentage as per the IEEE is 2.5. Therefore, that is also not acceptable. Now, let us see same condition. Therefore, what is very important is when all the individual harmonic current injections are at maximum, both voltage and the current distortions are violated when it comes to the TDD and also THD. Now, let us see what happens corresponding to the same percentage current injection. If the ISC by IL is 20, means for the same system, percentage current injection or the magnitude of the current that you are injecting is same, but system has become more strong. Now let us see what happens. Therefore, the next condition is the source has become stronger, that is ISC by I load is 20. With this ISC by I load being 20, again the same type of calculation you do, that is source impedance will be 1 by 20. Corresponding to the fifth harmonic, it will be 5 into 0.05. Like that, up to 29th harmonic, the impedances are given. Harmonic current injection is same. It is same as ISC by I load plus 10. Therefore, the harmonic current percentage is same. It has not changed with respect to the fundamental current. The percentage is same. What it means is you are connecting a source from the harmonic load from the source which is weak to the source which is strong. What happens to the THT? That is 1.68. TDD, that is the total demand distortion remaining same 3.38, but acceptable limit is 4. Because the acceptable limit is 4, and then what is that it is you are computed at 3.38, now this system is acceptable. To conclude, for the same current harmonic injection, if the fault level is higher, that is the system is stronger, voltage distortion will be within the limit. What do you mean by this? Assume that there is a utility and there is a consumer. If at all consumer is injecting the higher currents, ISC by I load is weak, therefore it is better to connect at the higher voltage level. It is better to connect at the higher voltage level so that actually at the PCC point of common coupling where many consumers are getting connected, with the utility bus, that is a stronger voltage level bus, then what will happen is the distortion levels will be coming down. Therefore, current distortion is a consumer perspective. Consumer can only control the current distortion. Voltage distortion is utility perspective, which implies utility has to ensure that the voltage distortion is within the limit and the consumer has to ensure that current distortion is within the limit. If the utility finds that particular consumer is injecting the current and as per the ISC by IL that is higher, or even if it is acceptable, voltage distortion is coming higher because there are many consumers getting connected, what he has to do is he should try to see that actually a person injecting the harmonic current, he has to provide the filter or get connected with a higher voltage level. You might have seen that actually most of the steel plants, when actually they were connected at 132 kV level, maybe the voltage distortion was higher because the fault level ISC by IL was lower. But when you get connected at the 220 kV, where actually the fault level is more and the IL is less, because at 132 kV current to the 220 kV current, IL is less. It may so happen that actually distortion will come down. Therefore, those polluting loads, we should try to see that actually get connected at the higher voltage level with looking into the various economics, so that actually the current distortion, even though it is with the user acceptable order, voltage distortion gets limited. There is one more thing we need to understand in the harmonics, that is the background harmonics. Therefore, whenever we do the measurement at the industry, it may so happen that actually industry current distortion may be lower, but even then at the bus, where actually the PCC point of common coupling, the voltage distortion can be higher. In those places, if at all for a upcoming system we are doing the measurement, it is worthwhile if we are able to disconnect the industrial system, industrial consumer, and try to do the measurement to find out what is the background harmonics in the system without the consumer who is going to get connected. For example, in this case, assume that you have got a 132 kV source, 100 MVA, Z is 0.2 per unit. Z is 0.2 per unit on 100 MVA base. There is a fifth harmonic current, 2.5% you are injecting. Fundamental current is 437.4 ampere, because on 100 MVA base, 1 per unit current corresponds to on 132 kV voltage level 437.4 ampere. That is 100 into 1000 divided by root 3 into 132. That is what we are going to get, 137.4 ampere. When you inject this current, fifth harmonic current, 2.5% of 437.4 ampere when you inject through the source, you are going to get 2.5% voltage distortion. 2.5% voltage distortion, because 0.2 per unit your impedance. At the fifth harmonic, this impedance becomes 0.2 into 5, that is 1 per unit. With that 1 per unit impedance, you are injecting a 2.5% current. 2.5% current, therefore the voltage becomes 1 per unit into 2.5%, therefore it becomes 2.5% voltage distortion. Now, this is acceptable level for 132 kV. Assume that this 2.5% is acceptable now. Now there is a consumer who is injecting the fifth harmonic current 2.5% at the fundamental frequency on 10 MVA base. When this fifth harmonic current is getting injected here, because this additional fifth harmonic current is coming here, this voltage distortion becomes 2.625. With the background harmonic, this is a background harmonic. With this background harmonic current in the system, the initial distortion was 2.5%. Now, with the fifth harmonic current being injected here, the distortion becomes 2.625. 2.625, which actually is increasing. Therefore, a particular consumer may not be the culprit, because his harmonic current is still within the acceptable limit. Whatever the harmonic current he is injecting is still acceptable to him. But because the background harmonics in the grid already at the PCC, even a small current he is injecting, it may actually deviate the acceptable harmonic voltage limits. Therefore, what actually utility could have done? Rather than asking this consumer to get connected at this PCC, they would have identified some other PCC where actually the distortion is less. That is what actually is very important. The current order distortion, current harmonic distortion is the consumer perspective. Consumer can only control how much current he is injecting whether it is within the IEEE standard, IEEE 519-2014. But whatever the voltage distortion is coming here, that is because of the various other consumers. Therefore, the voltage distortion is the utility perspective that we need to clearly understand. Therefore, what we are going to do is we are trying to understand a typical industrial system having two consumers at the PCC, point of common coupling. From the harmonic perspective, consumer 1 is dirty, means he is polluting by injecting the harmonic current, and consumer 2 is a very clean load. Illustration is done with only fifth harmonic current just to understand the concept. Two cases are simulated. One is with the source fault level corresponding to the strong, and also the other one with the weak source. We'll also see how to do the harmonic power flow, how to find out the series resonance, and mitigation methods we will try to discuss. So this is the system that has been considered. Afterwards, I will simulate using the MiPower, but each and every screen is clearly taken from the MiPower so that the concepts are very clear. This is a 66 kV grid. Fault level 3 phase is 1000 MVA. X by R ratio is 20. Then this is the consumer here, who is actually has got a fundamental current of 300 ampere, fifth harmonic current 10%, that is 30 ampere. 10% of 300 ampere, that is 30 ampere is the fifth harmonic current here. This is a non-linear load. 5 megawatt at 0.9 power factor. And this is the transformer 10 MVA 8% impedance DYN1, so that X by R ratio is taken as 20 for this transformer. This is a 66 kV dark conductor, the typical line. That is how actually this transmission line is considered. Now coming to the clean consumer, this clean consumer has got a load at 8 megawatt 0.8 power factor. He has got a 10 MVA transformer, 8% impedance. He has got a 10 MVA transformer at 8% impedance. And then he has got a capacitor bank also 5 MVA 11 kV. We will consider two cases, one with the mere capacitor bank 5 MVA 11 kV. The other condition is a capacitor bank with a reactor, current limiting reactor. Therefore, first case what we are going to do is we are going to consider a capacitor bank 5 MVA 11 kV with his load 8 megawatt 0.8 power factor. Therefore, 8 megawatt 0.58 power factor, whatever the reactive power is required here, is being compensated by this 5 MVA capacitor bank, and he is a very clean consumer. And this consumer is a dirty consumer who is injecting the fifth harmonic current. You may not like that word dirty, but from the point of harmonic distortion, he is a dirty consumer. Now, I load is a 50 ampere. Therefore, first and foremost thing is you do the low flow at the fundamental frequency. Once you do the power flow for the given system at the fundamental frequency and plot the current, you will be able to find out what is the I load at each and every point. Therefore, what is the I load here? 50 ampere, because 300 ampere here, and it is a 66 kV bus, 66 by 11. Okay, therefore 300 ampere, that corresponds to 6 times, that is actually 50 ampere here. 50 ampere will be the fundamental current at 66 kV bus. Similarly, the fundamental current here will be 300 ampere. The fundamental current corresponding to the load given here, including the capacitor bank, is about 71 ampere there. Therefore, when you do the low flow analysis using our MiPower software and plot the result in the ampere and angle, not in megawatt and MVR or kilowatt kVR, when you plot the results in ampere and angle, you will be able to know what is the I load. Therefore, I load here is 50 ampere. To do the short circuit study, short circuit study is going to tell you what is the ISC, I short circuit current. Therefore, the total short circuit current here is 8702 ampere, 66 kV grid, 1000 MVA fault level, Therefore, you are going to get the short circuit level as say 8700 ampere, 8702 ampere. What is ISC by I load? Therefore, 8700 divided by 50, ISC by I load is 174. What you need to do is, with respect to this, you have to check, go back to the IEEE standard and find out what is the acceptable fifth harmonic current distortion. For a 66 kV system, when the ISC by I load corresponding to 174, if you see the chart, the acceptable current harmonic distortion is 12% and acceptable fifth harmonic voltage distortion is 3%. Therefore, 12% is the current distortion that is acceptable and 3% is the voltage distortion that is acceptable. Now let us see what happens. The first and foremost thing in the harmonic analysis is to draw the frequency scan. Frequency scan is going to tell you, is there any series resonance in the system or is there any parallel resonance in the system? Now let us see what will happen at bus 1 when you do the frequency scan. At bus 1, you try to see, that is, you keep on increasing the frequency. In our software, there is a facility where you can do the frequency scan. That is, for example, fundamental frequency to the 100th harmonic frequency. The frequency is increased. You are going to form the Y bus corresponding to the harmonic frequency. Invert that, you are going to get the driving point impedance at the Z bus. The diagonal bus is going to give you the harmonic frequency driving point impedance Z bus. Therefore, when you plot that with respect to the bus number 1 frequency scan, let us see what happens. Therefore, grid 66 kV impedance, that is shown in red color. The frequency scan with respect to the harmonic order, impedance, if you see, the impedance started increasing up to 4th order harmonic. At the 5th order harmonic, that is at 250 Hz, impedance is minimum. Impedance is minimum. Then again it started increasing. Minimum impedance means a series resonance condition. Maximum impedance means a parallel resonance condition. Therefore, here what is happening, there is a series resonance condition corresponding to the 5th harmonic. At the 5th harmonic, there is a series resonance condition. Therefore, at the 5th harmonic, there is a series resonance condition. You will be able to know that at the PCC, at the grid bus, there is a series resonance condition because the 5th harmonic impedance is minimum. So let us find out why that is happening. Then you also plot the harmonic current now. You plot the 5th harmonic current. We have decided that it is a 300 ampere. 5th harmonic current is 30 ampere. Therefore, it is a 10% of 300 ampere is 30 ampere. Therefore, in the MiPower software, when you plot the harmonic current, you will be able to see corresponding to the 5th harmonic current, what is the current flows. Therefore, you are injecting 30 ampere current here. That 30 ampere current, reflected current at the 66 kV is 5 ampere. Therefore, 5 ampere you are injecting here. Now it is finding two paths. One is the source, other one is the consumer, who is a clean consumer. Now let us see what is happening. This 5 ampere current, what you are injecting here, rather than going to the source, it is getting absorbed by the clean consumer. Why? Because there is some resonance happening at that PCC. Now let us see why that resonance is happening. If you see why that resonance is happening, this capacitor is a 5 MER at 11 kV. Therefore, capacitor is on 5 MER at 11 kV and 10 MVA base, it becomes 2 per unit because it's its own. It is 1 per unit on its own base, 5 MER. Therefore, on 10 MVA base, it becomes 2 per unit. 5th harmonic XC becomes minus 0.4 per unit. Because XL is equal to 2 pi FL, X is equal to 1 divided by N into 2 pi FC. Because of that, Xc becomes minus 0.4 per unit corresponding to the fifth harmonic. Now you see this transformer. Transformer is a 10 MVA 8% impedance, that is 10 MVA 0.08 per unit. At the fifth harmonic, transformer impedance becomes 0.08 into 5, 0.4 per unit. What it means, at the fifth harmonic, this transformer impedance, reactance of the transformer or the XL value is getting negated with respect to the XC value, which implies this becomes a low impedance path. He is a very nice consumer, no fault of his, but the fifth harmonic current injected by the person here, neighborhood person, is being absorbed by here. What will happen? He will have an additional heating effect in the transformer, additional losses in the transformer. There will be a over voltage in the capacitor bank, and this capacitor bank, okay, capacitor bank is again trying to inject the, because if there is a voltage here, the capacitor bank is also going to inject the current. Therefore, this circuit is going to resonate. Therefore, whatever the current is there here, it is getting absorbed here, because the entire current, fifth harmonic current, is getting absorbed here. This is what we call it as series resonance problem. This is very important for us to understand. Therefore, the basic fundamental of the harmonic analysis study is to find out, is there any series resonance in the system? Is there any parallel resonance in the system? Now let us see what happens corresponding to the fifth harmonic limit. Therefore, this is the plot of the total demand distortion and also the total voltage distortion. Therefore, within the limit, acceptable limit is 3%. Okay, acceptable limit is 12%, what we have seen there. But the distortion here is 10%, because the fundamental current was 300 ampere here. The injected was there, therefore it is only 10%. And corresponding to the voltage distortion is acceptable is 3%. Compare that with respect to the voltage distortion, whatever you are getting here. Therefore, both are acceptable. But what is not acceptable? Entire harmonic current is getting absorbed by the good consumer. What this consumer should have done, therefore? Assume that this consumer has come first. He doesn't know that someone else is going to pollute the grid later, and then he's going to be the culprit. This consumer is going to be there, and he is getting penalized. What he should have done is, rather than having a 5 mA capacitor bank, he should have actually had that capacitor bank with a series reactor. Advantages having actually the current limiting reactor is, one is, when you energize the capacitor bank, over voltages will come down because you are energizing along with the reactor. Also, the injection current means the inrush current is also going to come down. Therefore, there is one more advantage. Other advantage is, you are going to tune that corresponding to the non-characteristic harmonics. For example, fourth order harmonics is a non-characteristic, because normally whenever you are using a power electronic equipment like the 6 pulse converter, the predominant harmonic current is 5, and normally we will not have actually, for a perfect symmetrical current waveform, we will not have any even order harmonics. You do the Fourier transform DFT onto the symmetrical waveform, you will find out that actually the even order harmonics will not be there. Therefore, what he should have done, he should have designed a current limiting reactor. Therefore, now let us see what happens. You can also plot with respect to the bus numbers. What is the percentage distortion? Therefore, corresponding to the bus number 1, 2, 3, 4, 5, corresponding to that, you will also be able to plot actually the harmonic voltage distortion. Now, assume that the consumer is going to limit the current inrush by having actually the 6% current reactor. Assume that 6% current limiting reactor, if you are designed, what will happen? It is a 5 mA on its own base. Xc is 1 per unit. XL is 6% of Xc, that is 0.06 per unit. at resonance frequency, NXL becomes XC by N. Therefore, N square corresponds to 1 by 0.06, that is 16.67. Therefore, square root of that is approximately 4. What it means is, 4th harmonic currents are minimum in the system. Therefore, if you have a 6% current limiting reactor, this is going to resonate at 6th harmonic, at 4th harmonic. Therefore, compensation system acts as an inductive circuit. Therefore, up to the 4th harmonic, it is a capacitive circuit. Above 4th harmonic, this compensation system acts as an inductive circuit. Therefore, at the 5th harmonic, this becomes inductive. Therefore, again you try to plot the frequency scan now. If you try to see the frequency scan now, you can see that actually the frequency starts increasing, the impedance starts increasing. Where it is resonating now? It is resonating at 4th. Means the impedance is minimum. It is actually the minimum. Impedance is minimum. Again it starts increasing. Therefore, now if you see that 5th harmonic, corresponding to the 5th harmonic now, the impedance is not minimum. But again you try to see what is the current distribution now. You are injecting 5 ampere current here. Earlier, the maximum of this 5 ampere current was getting absorbed. It was getting absorbed by the consumer here. But now you have got a capacitor with and a current limiting reactor. Therefore, this circuit is not resonating at 5th harmonic now. Therefore, it is offering some impedance. Therefore, now you can see the maximum current that you are injecting here is going to the grid. Because the maximum current is going to the grid, the 5th harmonic voltage increases. Because this current multiplied by the source impedance is the voltage here. The 5th harmonic current multiplied by the 5th harmonic voltage here is the 5th harmonic impedance here is the 5th harmonic voltage here. Therefore, whenever actually the systems are being designed, one has to be very careful and then try to see that actually the proper systems are done. If this consumer had done a simple capacitor bank without the current limiting reactor, tomorrow he doesn't know that actually some consumer is going to come and inject a 5th harmonic current, and he has got a 10 mA transformer with a 5 mA capacitor. This circuit is going to resonate at 5th harmonic. The entire harmonic current he has to absorb. His equipment will be suffering. Therefore, this is very, very important to understand that series and the parallel resonance that may occur in the system is very important. Now you can see that when you plot the distortion, the voltage distortion has increased here. The current consumer distortion remains the same, but here actually the distortion has come down now. Therefore, he the culprit. This person was getting affected, this consumer was getting affected, but what he has done, he has now insulated his system. He has insulated his system by having a current limiting reactor in the beginning only, in the design stage itself. Therefore, whatever happens in the grid, he is not getting affected. Therefore, consumer 2 has no control on the grid changes. Better to design his system carefully such that he is not affected with the changes in the grid. Therefore, whenever we design an industrial system, whenever we design an utility system, we have to be very careful. This example could have happened in case of a utility system also. For example, this utility, assume that it is a utility system, 66 kV bar 11 kV, the normal utility transformer we are going to have, and also the 10 mA 8% is the typical impedance we are going to do. And then in order to compensate for the load here, you would have put a 5 mA capacitor bank. This is a utility system. And at the PCC, there is a consumer who is injecting the harmonic current. In this case, what is happening? Utility capacitor bank with the utility transformer is resonating at 5th harmonic frequency. You might have seen many places, if you don't do the studies like this and then provide a capacitor bank, that capacitor bank along with the transformer impedance may have actually the series resonance condition. When there is a series resonance condition, it may so happen that actually the capacitor bank is absorbing all the 5th harmonic current. Therefore, it can so happen that actually it is going to fail. There can be the over voltage, the insulation degradation, and also the overheating may happen. Now you can see the once again the various bus numbers. What is the distortion? Therefore, you'll be able to know that actually the distortion is within the acceptable limits. Now you see what will happen if actually you consider actually the weak grid. In case of a weak grid, 66 kV grid, fault level is 3-phase. Single end to ground fault again is 200 MVA. 3-phase and the SLG fault level is considered as 200 MVA. Therefore, it is a weak grid. Now, in case of a weak grid, what will happen? Current direction with respect to the voltage is important with respect to the voltage. Therefore, this is a weak grid here. In many measurements, it may so happen that actually whenever we do the harmonic measurement, we always see the magnitude of the current, but the current direction with respect to the voltage is very important. For example, with respect to the voltage, current direction here is going to tell you that you are injecting here. And with respect to the voltage, fifth harmonic voltage here, if you look at the current direction here, you are absorbing here. Therefore, the current direction is very important. In most of the time when we do the measurement, we just look at the magnitude. That is not just sufficient. With respect to the corresponding voltage, fifth harmonic voltage, you find out the direction of the fifth harmonic current. That is going to tell you whether you are injecting, whether you are drawing. Now, if it is a weak grid, what will happen? The current remains same, but let us see what will happen to the distortion now. Voltage distortion is acceptable, still within the limit. Current distortion is not acceptable because it is 7% now. What is acceptable limit is 7%, but the current that you are injecting is 10%. Therefore, it is not acceptable. This consumer has got a capacitor and an inductor. Therefore, for him, there is no problem. But actually, now we can see here, 10 ampere you are injecting here. Okay, the current distortion, 10% is the current distortion here. And this is not acceptable as per the IEEE standard now. What he has to do? He has to design a filter. Therefore, now let us get into the software and find out how to design a filter. Therefore, this is the system. Divyakala, can you just confirm? Are you able to see the MiPower screen?
Not yet, sir.
You are not able to see the screen?
Not yet, sir.
Are you sure?
Yes, sir.
we can, sir.
We can see, sir. We
Oh,
are able to
fine.
see, sir.
Okay,
Maybe it is at my end, it is slow, sir.
fine. Therefore, this is the system, whatever you have considered. Therefore, basically, I would like to say how to give the harmonic current here. Therefore, this is the harmonic current source. Therefore, you'll be able to tell that actually it's a fifth harmonic current. You can specify the harmonic current with respect to the base current, that is a 300 ampere, and either in per unit or in percentage or in ampere. Okay, you'll be able to give the absolute value or in the per unit or in the percentage. What we are given here, it is a 300 ampere. We are given the value in per unit and 10%. That is actually, okay, 10%, that is 0.1 per unit. This is how the fifth harmonic current is getting injected here. Now, you can see the case here, 5 mA capacitor bank is there. Afterwards, we'll try to put the case here. Therefore, 30 ampere is getting injected. Therefore, when you look at the harmonic analysis study, you can see the frequency scan here. Therefore, this is the frequency scan. You will be able to do the frequency scan corresponding to the given bus. Therefore, you'll be able to select the buses and then ask for the frequency scan. But grid 66, let us see what is the frequency. Now you can see that actually at the fifth harmonic at the grid bus, the impedance is minimum. This impedance minimum means actually you are going to tell that actually there is a series resonance condition happening there. That is why actually the impedance has become minimum. Now instead of that, assume that we have gone for actually the current limiting reactor. Okay, you have gone for actually the current limiting reactor. Now you can see that the capacitor bank is still 5 MVR with a 6% current limiting reactor. The fundamental low flow is plotted. Now again see what will happen in the harmonic analysis. Frequency scan is selected. Now you can see at fifth harmonic impedance is high now. At the fourth harmonic it is resonating because that it is providing actually the resonating. Therefore actually the impedance is minimum at fourth, but we are not injecting the fourth harmonic current because normally the non-characteristic harmonics will not be there. Therefore there will not be any problem. This is what we need to check. Therefore first and foremost thing in the harmonic analysis is we need to do the frequency scan plot. That is going to tell you will there be any series resonance or the parallel resonance. And you can plot actually the distortions in the harmonic analysis. Therefore, you'll be able to see basically the various distortions here. For example, here the distortion is 10% current distortion. How to read is current distortion is 10%. Corresponding to that, voltage distortion is 2.64%. 2.64%. Same current distortion carries away here because the load current IL is same here, whether IL is here or here is same. Therefore, IL with respect to that, the harmonic current, the distortion is same here. And then actually with respect to, now you can see here, because you have got a current limiting reactor here, corresponding to that, the distortion has come down here and the voltage distortion is 0.26 per unit. Now let us take a case where the source fault level is less. I think this is not the case. Let me just close. Okay. Therefore, in this case, the fault level is less. ISC by IL is lower because the fault level is only 200 MVA. Now let us see what will happen corresponding to that without a filter. Afterwards, we'll design a filter. Therefore, without the filter, what will happen when you do the harmonic analysis? Okay. This is a 5 megawatt load, non-linear load. 0.9 power factor. Therefore, the reactive power is about 2.5. Okay, 2.5 will be the reactive power here, and this is corresponding to the low flow analysis. Now we'll see what will happen corresponding to the the distortion now. You can see here the distortion is again 10% only. But what is acceptable now? Because the ISC by IL has reduced now, the acceptable limit is only now 7. But how much you are injecting now? 10.07. It is not acceptable as per the standard. Therefore, what this consumer has to do now? Because this ISC by IL, with respect to that, the current distortion is not acceptable, he has to design a filter. How to design a filter? This is basically a 5 megawatt 0.9 power factor. Therefore, it requires about 2.5 MVR. Therefore, you can design a filter here which is going to resonate at fifth harmonic. At fundamental frequency, this filter is going to give 2.5 MVR at 11 kV, and at fifth harmonic it is going to resonate. Therefore, what can be done is we can try to see that actually we can design a filter. There is a facility in our software MiPower to design a filter. Therefore, what I will do is I will okay, you can design a filter here. That is, you just tell what is the harmonic order, what is the voltage 11 kV at fundamental frequency. Okay, how much MVR this filter has to inject. Therefore, we want 2.5 MVR at fundamental frequency. Q factor for the filter, we can take it say around 20. Normally, it will be around 20 to 40 or 50 based upon actually the reactor X by R ratio. That Q factor gets defined. Therefore, you will be able to check actually, okay, how much you would like to have the Q factor. That is going to tell you how steep the resonance point is going to happen. Therefore, the Q factor defined here is about 20. Therefore, what is that you are going to tell here? There is a fifth harmonic filter. You are going to design a fifth harmonic filter and at 11 kV, and at fundamental frequency it is going to give 2.5 MVR. The filter resistance, inductance, and the capacitance are calculated. Normally, if you want to design the filter corresponding to the higher voltage level, say 12.5 kV, you can still do that. Okay, then actually at 12.5 kV, because most of the 11 kV capacitor banks are rated at around 12 kV or 12.5 kV. You can always give that values also. But at fundamental frequency, what is the reactive power is there, that gets computed now. Now with this filter value, let us again do the load flow analysis. Now you can see the load reactive power requirement is 2.4 MVR, around 2.5 MVR. Filter is giving at fundamental frequency 2.49 MVR. At fundamental frequency, it is acting as a capacitor. It is acting as a capacitor. Therefore, this capacitor is actually acting as a capacitor. Therefore, that. Now, if you plot the frequency scan now, what should happen? At bus 3, if you plot the frequency scan now, at bus 3, it should so happen that actually frequency should, the impedance should be minimum, because it's a resonance condition. Therefore, let us see what will happen if you plot the frequency scan corresponding to bus 3. You can see here now, at the fifth harmonic, this impedance is low. Means entire harmonic current, now whatever the fifth harmonic current is there, that is being injected, will be absorbed by that filter, because actually it is resonating now. Okay, the impedance is low at fifth harmonic, therefore it is resonating. That can be seen here also. Once you do the harmonic analysis with this filter, you will be able to see what happens. Now you can see the entire harmonic current here is getting absorbed by the filter, and you can see here earlier this distortion was 10%, acceptable was 7%, this distortion was 10% earlier, now it has become only 0.81%. Therefore, in the harmonic analysis study, what is very important is trying to find out the frequency scan and find out either any series resonance, parallel resonance condition, and then based upon that, try to do the analysis. Now let us also see one example with respect to the parallel resonance condition. This is a simple illustrative to tell when actually the series resonance may happen, when actually the parallel resonance may happen. Therefore, this is a system with a 500 MVA fault level here, and there is a 10 MVA capacitor bank here. Therefore, this is the source, and there is a load here, which is a nonlinear load. You can see here, this is a 20 megawatt at 10 MVA, and it's a nonlinear load. And this nonlinear load is injecting the 5th, 7th, and the 11th harmonic currents. 5th is 3%. Fundamental current is 1000 ampere. The percentage is 5th is 3%, 7th is 1%, 11th is 0.5%. 5th, 7th, 11th, 3%, 1%, 0.5%. What actually you expect? We expect that with respect to the 5th harmonic, 7th is less, only 1%, and the 11th is 0.5%. Therefore, the voltage distortion also should be less. Voltage distortion also corresponding compared to 5th harmonic, 7th should be less. That is what we expect. Therefore, let us see what, let us do the harmonic analysis. Therefore, harmonic analysis. And let us look at the graph. Okay, we are going to see the voltage harmonic distortion at a particular bus. What we are expecting that actually corresponding to the fifth harmonic is 1.182 voltage distortion. Okay, and the 7th harmonic is 13.273, and the 11th harmonic is again 0.182. Therefore, the 0 here basically it corresponds to the total harmonic distortion. That is the square root of this plus square root of this plus this square 1.182 square plus 13.273 square plus 0.182 square. Okay, square root of that is 13.318, very close to that only. Therefore, what actually you are going to see here, you find that actually compared to the fifth harmonic, seventh harmonic current is very less. It is 3%, but it is a 1%. But even then, this voltage is distortion is very high. Whenever you see that actually the higher order harmonic somewhere, the voltage distortion has suddenly increased, it means that there is a parallel resonance in the system. Parallel resonance in the system. Now, again, if you try to see the plot of the harmonic current, okay, plot of the harmonic current, and then try to see what will happen. Therefore, we'll do one more example now. The frequency scan. You look at the frequency scan now. At the seventh harmonic, the impedance is maximum. Whenever you see a minimum impedance, that is a series resonance condition. Whenever you see a maximum impedance, that corresponds to the parallel resonance condition, which implies at this system, at the seventh harmonic, there is a resonance condition, that to a parallel resonance condition. Now let us understand why that parallel resonance occurs. This is a 500 mA fault level and you have got a 10 mA capacitor. Resonance point is square root of 500 divided by 10. That is square root of 50. Square root of 50 is very close to 7, correct or not? Because 7 square is 49. What it means is, in this system, you are injecting a current here. It has got two parts, parallel path. One is actually the inductive part here, and this is a capacitor here. There is an injector current with a parallel shunt inductor and shunt capacitor. But these two inductor and capacitor at the seventh harmonic are resonating. It's a parallel resonance condition. You are injecting a current there, seventh harmonic current. What will happen? It is offering a very high impedance for the flow of the current, which implies the seventh harmonic voltage will increase. Therefore, in the harmonic study, it is also important for us to understand when the series resonance will happen, when the parallel resonance will happen, and based upon that, our software has got all the facilities to understand the various conditions like the series resonance and also the parallel resonance conditions. I think I would like to stop now, and if there are any specific questions, I would like to take it. Therefore, basically, would like to conclude that actually in the harmonic analysis becomes very important for the system design, and then wherever the nonlinear loads are there, for example, arc furnace load or the welding system, induction furnace, and also the power electronics equipment, drives are there, hot strip mills are there, and nonlinear loads, they generate the harmonic current. Nowadays, more and more renewable energies are coming, even they will also generate. Therefore, what you have to do is from the manufacturer spectrum or the measurement spectrum, you try to find out the harmonic current, put that as a current source corresponding to the nonlinear load, inject those currents, then you'll be able to find out basically how the harmonic distortions can be minimized. Therefore, if at all any specific questions are there, I would like to take now.
Yes, sir. Thank you so much, sir, for that enlightening session on harmonic power flow, how it occurs, and what's the frequency scan, and the other case studies using which you've shown the series resonance and parallel resonance. We have a couple of questions here today, sir. The first one is from Mr. Rohan. The question is, in residential project, where should I place the harmonic filter?
Normally in the residential projects, if at all you want to place the harmonic filter, it depends upon the connectivity, whether you are taking the 11 kV supply or at the 415. You can always provide, if at all you have taken a dedicated transformer, you can always provide a filter at your 415 volt bus. But again, normally, is it required? You have to find out. Is it really required? Because ISC by IL, if you take corresponding to the residential, your load current is very less, and also the short circuit current will be very high. Therefore, ISC by IL, if you take, it will be somewhere around 1000. Therefore, corresponding to that, harmonic current, that is what you are getting to injecting, will be more or less acceptable as per the standard. Therefore, if at all you want to still look into that because of a problem is there, then better actually at the secondary of the transformer, in your distribution transformer, you can provide a filter depending upon the various other studies that you would like to have. Because 415 volt is sufficient, you need not go for 11 kV.
Thank you very much, sir. I guess that answered Rohan's question. The next question is from Rashmi Shekhar. And the question is, when we are talking about IAC by IL, whether IL has to be at the maximum load?
Yes, as per the standard, it is very clear. When you take ISC by IL has to be at the maximum load current. See, this is very important for you to understand, Rashmi Shekhar, that assume that actually your load current is 100 ampere. You are injecting a harmonic current, say for example 2 ampere. What is the percentage? Is 2% distortion. But assume that actually your load current, because your system distortion, although things overloading, everything is with respect to the 100 ampere. Because with respect to the 100 ampere, that is the maximum load current, the 2 ampere is going to increase your RMS current. Now, assume that you are corresponding to that some other measurement condition, the load current is only, for example, 2 ampere. Basically, say for example, at a very low condition, you are trying to fire the transformer, the 6 pulse converter at a very high angle, because the load current is very low. This load requirement is very low. Therefore, the current is only 2 ampere. The current waveform gets distorted. The harmonic current may be 1 ampere. What is the distortion you are going to see? Distortion on 2 ampere, it is a 1 ampere current. Therefore, you are going to see a distortion of 50%. But on 100 ampere current, when you look at actually the distortion, okay, it is very less. Because that 1 ampere on your fundamental current of 2 ampere, whatever the distortion, it is not going to change actually your voltage distortion. Therefore, this is very important for you to understand that when the current is very low, there will be the distortion which will be much higher. Therefore, the standard is very specific. At the maximum load current, you have to find out actually the to what extent the distortion is there. In between, you get a spike. You should not bother about a small spike that you are going to get. What is the maximum ISC by IL corresponding to the maximum load current? You try to find out, and then try to find out based upon the statistical analysis. Actually, look at the spectrum and find out how many duration, what duration actually it is more. Even that is very important. Next question, please.
So there are not much questions, but there's a continuation of the same question from Rashmi. Suppose if there is a minimum IL and we get a higher distortion level, then what would be the implications on the system?
Nothing will happen because there is no overload. And with a small current, IL is very low and there is a current. With respect to that current, your voltage will also not get distorted. Because ISC by IL now, the short circuit current when you take, it is actually very high. Therefore, there will not be any voltage distortion. Finally, for the utility perspective, voltage distortion will be still acceptable. Therefore, it is not just the current distortion with respect to the current that you have measured. You should always try to look from with respect to the maximum load current that normally you see in the system. That is very important.
Thank you so much, sir. And
because the overload. I remember in one of the project that we had done in Bahrain. Okay, there was actually the electric furnace. they wanted to connect submerged arc furnace. If I am right, it was a submerged arc furnace. They wanted to run that submerged arc furnace with a 25 MVA power plant without the grid connection. Submerged arc furnace rating was about 15 MVA. Means that generator is getting loaded only up to about 15 MVA, not more than that. We allowed a higher order harmonics also. As per the standard, if you see, we should not have allowed. But because the transfer generator is only loaded about 15 divided by 25 MVA, 15 MVA divided by 25 MVA, because the generator is loaded, even if the current distortion is about fifth harmonic current or the other current distortions are much higher, nothing is going to happen in terms of the overloading of the generator or with respect to the voltage insulation levels. Therefore, taking those things into account, we allowed the higher current because the machine was not getting loaded. Therefore, all these things are important because at the maximum load current, if you try to inject the harmonic current, there is a overloading, there is additional losses. And also the voltage distortion is going to degrade the insulation level. That is why it is very important with respect to the maximum load current only, all these things have to be accounted.
Thank you so much, sir. And there are a few other questions which have popped up now. One from Anil Vaidya. The question is how to get the fault levels of actual utility bus, say at 33 kV level.
Fault level, if you want to get, you need to do the short circuit study. What you have to do is you have to model the entire system. Normally, the utility planning department will be able to give the fault level at the higher bus voltage levels. For example, whenever they plan their system, for example, you are getting a connection at a 110 kV bar 33 kV or actually 132 kV bar 33 kV. When they do the short circuit study as part of their planning exercise, they would have given actually what is the fault level, both minimum and maximum at 132 kV bus. Now from 132 kV bus, you know what is the fault level. Therefore, you can always put that as an equivalent source there. Then you have got 132 bar 33 kV transformer. You know the impedance of that. And then from 33 kV, there may be a 33 kV line. You know that impedance. Then your 33 bar 11 kV substation will be there. Therefore, taking that impedance, knowing the source fault level, using the short circuit study, you will be able to do, or doing a small hand calculation also, you will be able to find out, because finally it is the driving point impedance or the Thevenin equivalent impedance. Because how to do that driving point impedance? You will be able to do the Z-bus building process or formulate the Y-bus and invert that. Then you are going to get the driving point impedance. That is the equivalent Thevenin equivalent impedance that you see from that point towards the source. Like that, using the short circuit program, you will be able to compute the driving point impedance. 1 by the driving point impedance is going to tell you the fault level. Three-phase fault level is given by pre-fault voltage 1 per unit divided by Z1. That is actually the driving point impedance. Single into ground fault current is given by 3 into pre-phase fault pre-fault level. That is normally again 3 divided by Z1 plus Z2 plus Z0, where Z1 is the positive sequence driving point impedance, Z2 is the negative sequence driving point impedance, and Z0 is the zero sequence driving point impedance. Therefore, for the unbalanced fault, you also need to build the zero sequence and also the negative sequence impedance diagram. But normally, the negative sequence, we take it same as the positive sequence. Therefore, only the zero sequence impedance is required. Hope I have answered it. Thank you.
Thank you so much, sir. And the next question is from Hari Krishna. Does large integration of electrical vehicles have any impact of injecting harmonics to the grid?
Yes, basically the charging stations where we have got a fast charger or a slow charger, in fact, actually they are going to inject the harmonic current. Therefore, we should be very careful whenever we select those chargers, because tomorrow maybe all residentials, we can have actually the 5 ampere socket and start charging our vehicle, two-wheelers and all. Definitely it is going to have some impact, but studies have been done, and then we have to see that actually these charging, whatever the chargers are there that we use, whether it is a slow charger or a fast charger, we have to ensure that current it is going to inject, okay, the harmonic current it is going to inject should be within the acceptable limits as per the IEEE standards. But
Thank you very
definitely
much.
one needs to do the studies. It is very important. In fact, we did one study. What is the effect of the solar PV, rooftop solar? Maybe about 5-6 years back for the BESCOM, we have done the studies. What is the effect of the rooftop solar harmonic current injection, whether it is acceptable? One is by the measurement and then extrapolating the measurement for the entire population. That is, what you can do is, where if there is a charging station, go and measure it, or the supplier of the charger, he is going to give the harmonic spectrum. Try to see that if the many consumers are injecting that, what will happen. Therefore, that becomes one of the challenge, like the PV injection. But mostly over the period, these chargers are also going to come out with actually the better standards. And also, being a power electronic equipment, I can always have within that a good charger supplier. He can also have actually the active filter component. Active filter means you find out what is actually the harmonic current drawn by the load and then try to inject a current which is 180-degree phase shifted dynamically. Once you do that, you are going to draw the fundamental frequency current, no distorted current from the source. Therefore, maybe over the period, if the pollution levels are increasing, then there may be a competition and then people may come out with actually the charging station, which has also has got a built-in active filter. So that actually from the source, it is always going to draw the fundamental frequency current, and then it can also have a compensation so that actually reactive power also it need not draw, and you can always operate at a unity power factor. Because the power electronics, so much of development has occurred in the power electronics, therefore you will be able to control both the harmonic current and also the reactive power drawal. You will be able to control. Maybe if someone is interested, they can always try to take up some project along with an academic institution and develop actually the indigenously. We also talk about the Atmanirbhar now. Therefore, you can also try to develop some of the things indigenously.
Thank you very much, sir. And the next question is from Mr. Jignesh. How to determine harmonic source or harmonic current direction based on the measurement data at individual load incomers?
So basically what you have to do is, whenever the harmonic measurements are done, it is not just the current measurement alone, you are also going to measure the voltage. Therefore, the most of the harmonic meters, they also give the voltage, magnitude and angle with respect to the fifth harmonic, and you are also measuring the current magnitude and angle with respect to the fifth harmonic. Therefore, with respect to the fifth harmonic voltage, if you see the fifth harmonic current, say for example, fifth harmonic voltage angle is say 10 degrees, and then fifth harmonic current angle with respect to that is say minus 10 degree, means with respect to the fifth harmonic voltage, this current is lagging, means it is your drawing. If you are going to inject, it will be leading current. Therefore, based upon that, the angular separation between the voltage and the current will be able to know whether you are actually injecting the current or drawing the current. Without that, it will be very difficult. Therefore, always you have to measure, look at the current magnitude and angle with respect to the voltage magnitude and the angle.
Thank you very much, sir. And the next question is from Mr. Gopalakrishnan. Is there any meter available to find the direction of the harmonic current?
So if you do any of the high quality spectrum or the harmonic analyzers, they always give actually the harmonic current direction. But most of the energy meter, whatever we are using, they also have a built-in harmonic measurement. To best of my knowledge, they don't give actually the harmonic current direction. They don't give. They just give actually the total harmonic distortion. But for example, fluke or any other harmonic measurements, okay, for example, the AR5 power analyzer, they always give actually the magnitude and also the angle. But normally we don't, actually you will be able to get the Excel dump. Therefore, what we do is we don't look at the angle, we just see at the magnitude. But magnitude is not sufficient to find out whether someone is injecting or drawing. It is always better to look at the angle also.
Thank you very much, sir, and I hope that answered his question. The next is from Mr. Sumit. In a network wherein we have grid substation PCC connected to an auxiliary network, some of them with rectifiers and traction network which has inverters and rectifiers, which network would be dominant source causing the harmonics at the PCC? Should I repeat the
again,
question?
it depends. At the PCC, you are telling that actually there are traction loads are also there. There are other consumers are also there. Again, you need to do the measurements only. You will not be able to know who is dominating. But normally, the traction loads are also going to inject the harmonic current. And also, if there are other consumers are also going to inject the harmonic current, because unless you do a measurement, you will not be able to tell who is actually dominating. There are two ways of looking at. One is actually you can go through the manufacturer catalogs, but what we have seen in with our experience is whatever the manufacturer they claim, but in the reality it may be slightly different because they have claimed those things with the ideal conditions. What is that ideal condition? For example, we tell that actually the vehicle is going to give 20 kilometers or 30 kilometers mileage per liter. It is a very ideal condition. How many times we are going to get that? Therefore, that is very important here. Therefore, what I suggest is try to do a measurement to find out. At least then we'll be able to know who is actually injecting the more current. And again, it has to be looked with respect to the ISC by IL. And magnitude. For example, I tell you, at the PCC, there is one consumer who is injecting 1 ampere current, 1 ampere harmonic current, say fifth harmonic current, and his fundamental current is only 1 ampere. How much current is injecting? 100%. Fifth harmonic current. Fundamental current is 1 ampere and he is injecting, say, fifth harmonic current. 100%. There's one more consumer whose fundamental current is 50 ampere, who is injecting 10% current. 5 ampere is injecting. From the grid perspective, which is actually going to affect more? From the grid perspective, this current of 5 ampere is going to affect more rather than this 1 ampere. Therefore, actually many times we feel that actually no, it's just a percentage. Percentage compared with respect to the absolute value is important. That is why IEEE standard clearly talks about ISC by IL. Because that 5 ampere is going to distort the grid supply voltage more compared to this 1 ampere current, because both are flowing to the same source with the same impedance. 1 ampere is not going to affect much compared to that 5 ampere. Therefore, these are all very important to understand in the harmonic study. Normally, what we do is, okay, percentage harmonic distortion is very high. But that very high with respect to the watt current is very important. Next, please.
Thank you so much, sir. And the other question is from Mr. Akash Aryan. While modeling harmonics, up to what order of distortion is important to consider?
See, again, if you look at the standards, okay, they always go up to 50th and also the 100th. Therefore, again, go by the standard. It's not that what is important, but thing is, if at all you have got a 6 pulse converter or a 12 pulse converter, normally what will happen is the predominant harmonics will be, so if it is a 6 pulse converter, it is a 5, start from the 5, 7, 11th like that. If it is a 12 pulse converter, the predominant harmonic will be 7, 11, anything. But if it is actually the electric arc furnace, normally it will also have a non-characteristic harmonics like second, fourth also. Therefore, depending upon the system, you will be able to find out. But what is important is, will there be any resonance at some higher order harmonics also? That is actually the parallel resonance. Therefore, it is very important. For example, what we have seen there, corresponding to the 5th, 7th harmonic, it is resonating. But see, rather than, for example, the frequency, whatever the capacity bank you put is 10 MVR, and the source fault level is 500. Therefore, 500 divided by 10, the square root of that 50, that is 49. Instead of 10 MVR, if you had a 1 MVR, it would have resonated at some other frequency. Therefore, it is very important, is there any resonance in the system? Frequency scan you have to see, and then are you injecting any harmonic currents corresponding to that you have to see. But invariably, most of the systems up to 21st or 27th harmonic, more or less will be able to find out that actually there is no problem. But assume that instead of a 12 pulse converter, you are using actually a system which is a 24 pulse converter. Then what is the predominant harmonic? It is a 23rd harmonic and onwards. Therefore, you have to look into the system, the equipment that you are using, and then find out what is the predominant harmonic from where it starts, and then based upon that you have to start looking into the various harmonic current for your measurement and also for the simulation.
Thank you very much, sir. And the last question is from Mr. Anurag Chaturvedi. He has 2 to 3 different questions. The first one is for VFD procurement, what shall be the PCC definition to convey to the vendor as per the IEEE 519 standard?
For variable frequency drive, VFD. Is it VFD?
VFD.
Okay. Yeah. Okay. See, for you, when you procure the VFD, for him at that voltage level only, assume that you are having a VFD. For example, you have got a boiler BFW motor or actually ID fan or FD fan in a power plant, 6.6 kV. You want to convert that ID fan or FD fan motor to a BFW, the VFD drive. Now, for you, the harmonic specification is with respect to that 6.6 kV only. Therefore, there for your 6.6 kV bus only, with respect to the ISC by IL, you have to tell actually what is the harmonic current. That is very clear, because again the equipment supplier, he is going to only talk about what is the current he is going to inject, and he has to ensure that that current that is going to inject at that level is within the limit. Now, assume that you have got many VFD drives at 6.6 kV and your PCC is at, say, for example, at 132 kV. You have got a 132 bar 6.6 kV or 132 bar 11 kV and 11 bar 6.6 kV. Then, if at all you have got a 132 kV there, you have to ensure that with all the drives, with respect to the utility, your current distortions are within the limit. But for the VFD drive supplier, the PCC will be at 6.6 kV only. Therefore, you need to check what is the fault level there, and based upon that, you can specify what is the distortion that is acceptable. Next question.
Thank you very much, sir. And the next question is, for solar PV plants, is it mandatory to perform harmonics if the inverter vendor is complying with the IEEE 519 standards? Again, the same question. I mean, the question is from Mr. Anurag.
Yes. See, the question is actually, at least even though they comply that they are within the limit, okay, it is better from the utility perspective or from the consumer perspective to ensure that, because the vendor has given, to ensure that actually those are all within the acceptable limit. Therefore, normally most of the utility, what they do is they try to see that some measurements are done, and then based upon that, okay, assume that actually some XYZ vendor has given an inverter, and then there are about 10 installations are there. They try to do the measurement at 1 or 2 installations to find out that whether it is within the limit, so that actually there will not be any problem when the same type of inverters are populated across the utility. In fact, that is why we did the measurement at the BESCOM, and then we found that actually more or less actually the current distortions are all, the current harmonic distortions are all within the limit. And but there was one more thing actually, there is actually the DC current offset. If there are 2 inverters are there, if actually the DC offset current is more, it will circulate among the 2 inverters. So therefore, we found that actually the DC offset current was actually slightly higher, because the DC offset current will circulate. Therefore, these are the things we need to check actually. Therefore, better to do the measurements typically in 1 or 2 places to ensure that whatever has been claimed by the manufacturer as per the ideal condition, they would have produced the CPRI or any XYZ, the research laboratory, the testing laboratory certificates, but at least to measure and then get yourself confident that yes, this is what is happening.
Thank you very much, sir. And his third question is it important to consider LES lights factor for harmonics, as quantum of these lights are high?
But LED?
LES. LES light. L as in line, E as in, I'll repeat that, sir. Is it important to consider LES lights factor?
I think LES light factor. I didn't. Is it LED or LES? LIGHT, how it is there?
Okay,
Can
sir,
you?
now he has typed it again. Mr. Anurag, would you like to talk, unmute yourself and ask it yourself? I guess it is LED lights, sir.
Okay, that's what. If it is a LED light, basically, yes. In fact, they also inject the harmonic current, but it can be looked into similar to your CFL. Okay, earlier CFL were also trying to introduce a lot of harmonic currents because actually the choke and also the capacitor being there. Therefore, I feel actually the harmonic current penetration from the LED lights to that extent has not severe. But anyhow, I don't have any experience with respect to the any measurement that has been conducted. Maybe the utility should try to look into that. What is the effect of the the LED lights? But more or less, to best of my knowledge, I think the harmonic current must be within the limit. But maybe some people can try to do some measurements rather than the housing LED lights. We may also have to look at the street lights. What is the harmonic current that we inject? But compared to the CFL and also the sodium vapor lamps, I think harmonic currents may be much less corresponding to the LED lights. But I don't have any ready experience. But it is a worthwhile to look into that and then do a comparative study how the harmonic current injected by the LED light compares with respect to the CFL or the sodium vapor lamps.
Thank you so much, sir. And I guess there are no other questions right now.
Okay.
It was really a pleasure, sir, to hear your answers, and thank you so much for your patience. We have a few announcements about the upcoming webinar, sir.
And before that, I would like to tell that there are some other few questions because of my busy schedule. I couldn't answer for the 2 other sessions which completed earlier. But definitely each and everyone will get the replay. And all these questions, okay, because we also are learning by the questions. Therefore, what we'll do is we'll try to consolidate all these questions or the typical frequently asked questions, something like that. And then we'll try to see that each and every question is answered and it is all actually qualified, and then we'll try to publish each and every question and the answers also, so that if you have if at all any better answers are available, better explanations are available, we'll try to put it, and then maybe next week by next week we'll get the answers for all the questions of the 3 webinars.
Thank you very much, sir. That was really very kind of you. And there's another question from Mr. Anurag, but I guess in the interest of the time, we will take it offline, sir. So we have a few announcements to make. So with your permission, may I proceed, sir?
Okay, you can proceed, Divya.
Yes, sir. Thank you. Dear participants, thank you so much for your patience. Though it is slightly above the scheduled timing, we appreciate your patience for staying back with us. We have the feedback form link that will be shared in the chat box. So kindly make use of the link and share your feedback there. And it's also a privilege to announce the next topic of the webinar that would be on neutral reactors design studies for shunt compensated EHV lines using MiPower product. So that brings us to the closure of this event today, and I take a moment to thank all the participants who have been consistently turning in for the sessions, and also the new participants who have shown interest from various sectors, and also the PRDC colleagues and my committee members who have helped in this organization organizing this webinar effectively. I thank you all once again from my heart, and please make use of this link to share your feedback. Thank you so much, and all of you have a great evening.
So thank you, Divakala. Thank you.
Thank you very much, sir. Have a great evening.